So what I'm going to do today is I'm going to finish the portion of the chapter 3 that I intended to cover. This is wrapping up how you build a satellite. From what you've seen last time, you saw that it's a very complicated process, and me trying to cover in 3 lectures what they spent 2 years in doing, is not even possible. But at least that gave you some idea, and then we'll put the focus on what we are studying here, and this is essentially the communication equipment. So I'm going to go over some of it today. Specifically, I want to spend a little bit of time describing some equations that talk about the antennas, because we're going to use them extensively in normal link budget and calculations just to properly dimension things. Now, what I showed you at the end of the last lecture was a single conversion. Remember, for a C, we had a C-band transponder, and we were able to go from roughly 6 gigahertz down to 4 gigahertz. So the channelization in the C-band, you are exactly 2.225 gigahertz apart. That's a relatively small jump when you compare the frequencies. You're going from 6 to 4, so you can usually do that in what we say single hop, right? You have one mixing stage that you carefully design, and which is relatively low in frequency, for which you can do the electronics, and it functions reasonably well. Now, for cases when you're operating very high in frequency, and in today's age, high in frequency means in this scenario 14 gigahertz or even higher, where you go 20, 30 gigahertz, then converting down to a lower frequency is not an easy task, right? Because what you need to do is not only down convert the signal, but you have to clean it up, you have to amplify it. So that means that there's a whole bunch of electronics that needs to work at the intermediate frequency to clean up the signal, to condition it so that you can rebroadcast. So what we do in those kind of it's cases, and it's not uncommon to have what is called two-stage conversion, or a double conversion transponder. Let me go through an example, and then I comment what is actually happening here. So I have here KU band log diagram. KU band is this 1411 gigahertz pair. And that means that you're receiving signal from the ground that comes in a 14 gigahertz band. And you need to convert it down to 11 gigahertz. So let's say you tried 11 gigahertz conversion. So you would have an oscillator here that's 2 point something, close to 3 gigahertz frequency. And you would have to kind of look at the difference, and then you would get down to 11 gigahertz. But the problem is you have now signal at 11 gigahertz, and you have to amplify it. So that means your amplifier needs to work at 11 gigahertz. All of your filtering stages need to be 11 gigahertz. And if you look at your transponder channel, it might be 30 megahertz, and your carrier frequency is 30 gigahertz. So your bandwidth is so small relative to your carrier frequency, so that your filter is really just an ideal, very, very narrow band filter. And designing those things, it's not easy if sometimes it's not even possible to get that kind of selectivity. So to make this thing work, what you see here done is you go from 14 gigahertz, you have a local oscillator, in this case, which is 13 gigahertz, not megahertz. This is a typo here. So you go from a carrier at 14 gigahertz, you mix it with 13 gigahertz, you eliminate the sum of the two, and you focus on the difference, and you end up at 1 megahertz, 1 gigahertz. 1 gigahertz is a relatively low frequency in microwave, and you can actually find a lot of components that work at that frequency that are relatively inexpensive, reliable, highly selective, good performing. You do all of your processing in that relatively low high frequency, and then before you get to transmit it, you up-convert it to the channel that you're trying to use, and then amplify it, and then send it out with the antenna. So that's a double conversion transponder. It's common whenever you're operating in high frequency because of the reasons that I just stated here. well, you can see here, there are all sorts of problems like emission requirements, non-linearities, everything. If you don't do it this way and you try to control all of this at the high frequency of your carrier, you're running a lot of problems. So double conversions are common for the high frequency operation. And then finally here is what I have is kind of block diagram of what I refer to as the regenerative responder, the one that does onboard processing. Here you have actually full receiver chain and full transmitter chain. You have a receiver, a demodulator means that you strip the carrier, you take it all the way to the basement. You bring it down to IF, you sample it at IF, do all the signal processing, demodulate, get your decode, it gets your ones and zeros, and then you have an onboard processing. And then what onboard processing means, you can maybe just short circuit, that's the simplest form of onboard processing. You just resend what you did. But a lot of times what that means is switching. You say, okay, you look at the address of the packets that you're receiving, you say, okay, this guy goes to a different location than this one. Usually when you have an onboard processor, processing capabilities, then you allow multiple beams that you have in your transmission systems, and you can reroute the packets to the different geographical locations based on their address. Because you have that luxury here. Your satellite is a switch. It's not a bent pipe anymore. It's not just taking whatever it comes and puts it at a different frequency. Now looks at what it's receiving, and then it can have ability to switch it to go different places. We talked about advantages and disadvantages. The advantages are obvious. You have a much more efficient system, but disadvantages are you are actually tied to whatever is the interface that you design. So unless you're using some flexible design and radio part, which is still upcoming technology, and disadvantages, it's more complicated, right? Based on what you've seen last time, in satellite world, we cherish simplicity the most, right? If you can do something with less components, more robust approach, then you do it that way. Because every time you add something, you have to test it, and you have to make sure that even though you added more things, it's still going to maintain the reliability so that it doesn't break over a period of 15 years. All right, so let me go talk a little bit more about how the frequencies are used. This is an example here. What I mentioned even at the beginning. The smallest allocatable unit in most satellites is what is referred to as transponder. You can think of a transponder as just the analogy is actually excellent, as a pipe, right? You have certain portion of frequency band that you feed into that transponder. It receives at one channel, transmits its counterpart, and it has a certain band. Although, nothing prevents satellite manufacturer to design any kind of bandwidth they would desire, right? They can do whatever they want. It's not like in a cellular world you don't have compatibility requirement, like that Nokia phone needs to work with Alcatel-Lucent infrastructure, right? Here it is common that you have satellite would work with any equipment that respects its limits, right? What is the frequency range, and what is the power range, and whatever you fit in within that pipe, because ultimately it doesn't care. It just takes the signal and puts it on the other end. But it's common that we have certain bandwidths. The most common one is 40 megahertz bandwidth, which is the channel separation. And then really out of that 40 megahertz bandwidth, you don't use the entire 40, you use middle 36, and you leave a little bit of guard band so that you can amplify without mixing and mixing the signals and the crosstalk. And then since the environment is essentially free space, we have the luxury of being able to maintain the polarization, right? A lot of you went through the audio propagation class where I said you transmit in one polarization, but because of all these reflections and multipart the signal goes through, you cannot hope to receive the same polarization that you transmit, right? And we talked about that you can have even multiple antennas that are orthogonally receiving so that you capture the polarized signal. Here you have a little bit of luxury of free space so that for the most part, if you send one polarization, that's what you receive. And we use that in a satellite communication so that we can reuse our spectrum more efficiently. So if you look at here, what I have is an example of 500 megahertz that we have in a C-band. And this is obviously downlink because it's a lower frequency, 3700, 4200. And this is an uplink, or I should say ground to satellite, which is in a 6 gigahertz range. And then what you do is you have channels that are 40 megahertz wide, but which are separated. Center frequencies are separated 40. Is it 40 megahertz or 20 megahertz? They're separated 20 megahertz apart, right? So the channel frequencies are separated 20 megahertz apart so that they overlap in a spectral domain. If you look at, for example, channel here 1 has a center frequency 3720. 3700 is the end of the band, so the carrier is at 3720. The end of this channel is 3740, but that's the central frequency of the next channel, right? So you have them kind of like this, right? This is the first channel, and then the second channel is right there, and then the third channel is right there, right? Now you can see that their overlap is substantial, but what you don't see in this graph is, well, it indicates that these are your horizontally polarized, and these are vertically polarized. So the ones that are horizontally polarized, that are on the same polarizations, they do not overlap, because here the only means of separating the channels is you're making them separated in frequency domain. That's how you can separate. V and H you can separate through polarization. So even though they're overlapping in frequency, because you're receiving on one polarization, there's a little bit of noise bleeding depending on how much your signal gets depolarized as it travels through the atmosphere, but you're able to tolerate that. So this is how in 500 megahertz of spectrum you can actually fit 24 transponders, each one of them having 40 megahertz. So if you were to multiply 40 times 25, because there's some guardrails, right? Then you end up with 1 gigahertz, which is actually 500 goes to one polarization and 500 goes to the other polarization with some guardrails on both ends of the spectrum. So this is what flies up in the air, right? How do you get these frequency bands? Well, there are 2 or sometimes 3 levels of management. First, you manage the frequency globally, and these are those ITU regions, right? ITU regions. We have ITU 1, 2, and 3. We are here in ITU region 2. And then that's just global allocation, but even though we allocate the frequencies globally, they're managed at a local level. So if you let's say launch a satellite and you get to operate, I don't know, let's say you are in ITU region 2, you get this. Your signal is going to be heard, let's say, both in the States and Mexico, United States and Mexico, right? But in order for your service to be available in both of these states, you have to actually have a permission for local frequency managing authority. So that means here you would have to have FCC's permission to sell the service in the United States, and then you would have to have a permission of appropriate regulatory body in Mexico as well. In ITU region around here, we're not I guess in terrible trouble, because there's just 2 or sometimes 3 countries to think about. But if you remember last time, what in that video, he was trying to cover Europe, and even though you have ITU 1 region there, there's 20, 30 countries that each one of them has an independent body that you have to get the approval to sell the service. So that means that I don't have to go knock on the door by door to get that service provision. And then when you, what is it that as a satellite provider, what is it that you sell? You sell transponder, right? You sell transponder time and the transponder band. And typically what you do is you sell the entire transponders, but there are some cases where you can get a portion of it, and you can say you use this much of the transponder frequency band, but then your limits on the link budget need to be really strict, so that because you end up having signals that are coming from different places that you need to mix, right? And you cannot allow, and we'll go through that later, that they're of the vastly different powers, because one can overpower the other. So you have to have a tight management of both power and out of band emission. And then I have a price here that typically, if you were to rent the transponder, you would pay about $2 million per year. So if you think about 24 transponders and how much that can cost, you can see that even though the launch of the satellite is expensive, ultimately they have to be making money, right? Because otherwise there would be no justifications for them flying around. Now, the biggest one thing that you're going to learn, a lot of you are in wireless. I think that almost all of you are in wireless. What you're going to learn about wireless systems in general is everything is I guess, can be worked out. And there's a lot of theory and science that helps you. And by everything I mean coding, modulation, synchronization, phase lock loops, and everything. But if you can't build the antenna, everything falls apart, right? So ultimately, everything boils down to the antenna, right? So here, so that's why even though they're I would say not when you look at it at the end, it just looks like a piece of tin or whatever they're made of. It actually is the make or break point of every communication system. So satellite antennas are very important pieces of the communication system. They're just here listed are some of the things that we use to characterize antennas, and this is just in general. I just want to put them in slide here so that you make sure you know what these are. When I talk about antenna gain, what the antenna gain is. Antenna pattern is the graphical way of presenting the gain, because antenna gain is a function of the two angle coordinates. Right? You have antenna gain different in every direction relative to the center of the antenna. We specify antenna gain usually through its pattern, which is three-dimensional, but a lot of times we represent it with two cuts, horizontal and vertical. When we talk about beamwidth, it's the objective of the design of the antenna is to focus the energy in a given location. You end up with a area of the space to which majority of the energy is traveling. The width of that area, angular width, is called beamwidth. What is its efficiency? How efficient it is the antenna in converting the conductive power, the power that you deliver to the antenna ports, to the radiating power, the power that you actually radiate in space. Its impedance, its reflective bisbar, and so on and so forth. So there are quite a few parameters that we use. In what we do here, we're going to be mostly concerned about the gain and efficiency of the antenna, and then obviously its size, because what we're going to learn pretty soon is that the ability of the antenna to focus the RF energy is directly proportional to its size. So the bigger the antenna is, the smaller portion of the space it is able to radiate. Now, antennas need to be lightweight, high gain. That's lightweight for obvious reasons, because you want everything that flies to be lightweight, and they have to be high gain, and that kind of comes hand in hand with narrow beam, right? Because if you remember, antennas are nothing but the passive device. Even though we talk about the gain of the antenna, it can never create any amplification, right? Because it's a passive device. All that antenna does You can think of it as a balloon. It takes all the energy that is delivered and then kind of squeezes it in particular direction. What that means is that because there's a more energy radiating in this direction, this is at the expense of the less energy being radiated in the other directions. And this is exactly what we want, because we want to radiate in one direction and spare all the other angles from radiations. We want them to be highly efficient, meaning that whatever we provide in terms of conducting power gets radiated, and then I'm doing the tunnels. And then we need them to preserve polarization purity. What is polarization purity? If we make the design so that it's, let's say, vertically polarized, we want to actually make sure that the majority of the energy, vast majority, is radiated in given polarization. This is not even any sorts of luxury here. It is necessity, because remember, we reuse polarization. So if you're operating on channel 1 and it says that you're horizontally polarized, you want the little, whatever you radiate in a vertical direction to be as minimum as possible, because that directly impacts somebody else's ability to reuse the channel 2. There are two kinds of antenna systems that you find on us, at least two kinds. There may be more if you have satellites that operate in multiple frequency bands. And there are antenna systems that are used for communication. And if you look at this out, these are these dish antennas, the horns and whatever high gain antennas that you have. They're servicing the signals that are of a high bandwidth, high data rate. Therefore, the operating margin about the channel limits is relatively small, right? So they have to be high gain. And then there are antennas that are used for management of the satellite, the control and monitoring. Those are the antennas that have relatively smaller gain. They usually actually work in a lower frequency ranges, because one of the things that you have to try to do is maintain the communication even with the satellite, even when it's not engaged in communicating data. You want, because through TTC&M system, you actually control satellite and you get the feedback on its health. So you want that to be at a lower frequency, and you want that to be as reliable as it can be. Okay, so there are some. So this is yet another slide on types of the antennas. As I said, for TTC&M systems, we use lower frequency ranges, and then we use wire antennas. Those are the simplest ones. You can use other types, and I've seen use horns, but they tend to be, more with a narrower beam, and that's not necessarily what you want there. Right? You want something that is less selective in the frequency domain. And then for the communication systems, you use horn or those are the antennas that they're called horn antennas because that's how they look like. They look like you have a feed and then you have a horn that can be either rectangular or spherical. And then you use dish antennas that might be fed with a horn, but then you have this reflecting surface behind that allows you to shape your beam. And although we look at those dish antennas and we assume that it's all, ideal, and that's parabolic dish or whatever is the surface there, you saw the last time that design of that reflecting surface is very precise task. And the reason for that is because you're rarely trying to, if you go with some geometric structure, regular geometric structure, your beam ends up being spherical. And that would be okay if you're trying to put a spot beam on the ground that is spherical as well. And sometimes we do that. Like in this case, this is a Viasat's Wild Blue, which is one of the K-band satellites. And this is what they try to do. They're kind of trying to make the frequency reuse and put the spot beams on the ground, right? And they need to be almost spherical, and therefore, regular parabolic dish with a regular architecture would do that. But a lot of times what we try to do is cover the areas of the ground that are not of regular shape, like in this case, you want to cover continental US, or in the case that we saw in the video, the guy was trying to design the reflective surface so that it covers the Europe, right? And Europe is not regular as well. And the way how you do that, you have your feed sends whatever it sends, and then you, through the reflecting surface and small changes in its surface, you actually shape what the pattern looks like. And this is an example of that. This satellite is to the right, so it's somewhere above the Atlantic Ocean. And this explains why this is elongated like this, right? So it's radiating from this direction. What is this line here? Why is there a line here? Why doesn't it continue all the way to the right? It's a very simple explanation. Why? Because the Earth is a globe, right? So this is your horizon. This is where you fall behind the horizon. So this is the radio horizon. So up to this point, you see the signal, and then it's very low on the horizon, and then you step in behind the horizon, and that's the line so that you don't see. The numbers that you see here are equi-power contours. When you generate these plots, what you present here are the contours of the same ERP. Right? So when I see here 51, that means when I sit on the satellite and I look at ERP in that particular direction, it is 51 dBm. Right? So everywhere in this contour, when I do link budgets, I can assume that my transmitter power on the satellite is 51 ERP. And then in this area here, it's 50, and then this contour here does 48. So everywhere in this contour is 48, and then here it's 52, and so on and so forth. So you can shape those, you shape them, based on economic criteria and your target objective, right? When you have, if you're, let's say, in the business of delivering data service, you want to have a good signal, then you would try to target, the areas where you know that you're going to have a lot of customers that are going to be sharing this particular band. You want to have a good signal there. And here, let's say, where you don't have any customers, then it is what it is, right? So you don't care.
Why is the maximum ERP over the ocean?
No, it's targeting West Coast, right? It happens to be over the ocean, right? Happens to be. You cannot really say, okay, go to the beach and then go further, right? It's trying to target. You can see how it's trying to target here. What is it? Chicago area, and then this is now Seattle, and then Houston, and so on. These population centers, right? And it's leaving Montana and Dakotas alone, whatever it ends up being. So, but this may be one satellite, but you have other objectives, right? This is trying to do it with one antenna. These days we're kind of moving towards this concept for two reasons, because you can provide more reliable coverage because you're now covering smaller area. You can focus the energy only there. And then the second one is you can reuse the frequencies. So you can now use the same frequency here and here twice, or many times throughout this area, and get a higher capacity than in this case here, because you have one antenna. But this would be more appropriate for like a data service where you're trying to deliver some sort of data connectivity and you're trying to maximize the capacity. And this would be more appropriate when it's a broadcast, when you're sending 24 channels of the TV and you want these 24 channels to be visible everywhere. And it's the same 24 channels. So different objectives have a different result in the different designs. But what I would like you to remember is they're essentially these kind of approaches where you have one antenna that covers larger area, and these are appropriate for broadcast. And then you have a spot beam approach where you're trying to maximize the reuse of your spectrum and try try to achieve this kind of pattern on the ground. And this is a single antenna. This is a cheaper design. This is what you saw in the video. The guy was doing. This is a much more complicated design because you have to have an antenna array with multiple horns and multiple reflecting surface to achieve this kind of thing.
So the spot size covered is multiple antennas on one satellite?
It's, yeah, correct. You have one antenna with multiple feeds, right? Multiple antennas, and then each
So
one of them.
Like 50 antennas on there?
Yeah, well, 50 beams. Okay, so here's some basic relationships that I would like you to know. The first one is a basic relationship that comes from electromagnetic theory that relates the gain of the antenna to its physical size. We kind of had this relationship in RF propagation where we call this A times nu A as an effective aperture of the antenna. And this is, here we say the effective aperture is some coefficient times the physical size of the antenna. Same, and this nu A we call aperture efficiency. So it tells you here that if you want to have a high gain antenna, they have to be relatively big. But relative big to what? Relative big to lambda. Relatively big to lambda. So the smaller the lambda, the antenna of the same size has a chance of making a higher gain, right? So that's why when we go to the higher frequency, it's not all bad, right? There are a lot of things that are getting progressively more difficult. But one thing that helps you is that for a given antenna size, you can have a higher gain by going to the higher frequency. And that kind of goes with the square of the frequency, right? So you have two things happening in parallel. When you go to the higher frequency, your free space path loss goes with 20 log of 20 dBs per decade, but you have two antennas on both ends whose, for the same size, have the gains that are growing 20 dBs per decade as a function of frequency. So it's actually going to the higher frequency, you may end up having some link budget advantages if you keep the antennas of the same size. So now if you take this general expression here and then take A as being antenna of a circular profile, you end up with this equation here, where D is the diameter and then lambda is the wavelength. And these two equations you want to have in handy because there will be a lot of problems that we do for exercise, and I'll do a few examples later in the class. So that's one aspect of the antenna, how big the gain you can achieve. The second parameter of the antenna is how narrow the beam can be, right? How narrow can you make the beam? And there is an approximative relationship that says that the 3 dB band, which is the point, the 3 dB beam, the point at which the beam falls 3 dB below its peak, is given as this one here, 75 lambda over Z. That's not always terribly accurate, but for all the calculations that we do here, we're going to use that. And it again tells you that the same thing here, that it is the relative size of the antenna with respect to lambda that allows you to focus the energy. And then the smaller lambda is relative to D, the smaller the beam that you're radiating becomes. And then if you combine these two relationships here, then you get exactly what we were talking about earlier, that antenna is a passive device. The only way how you can achieve the gain is by reducing the area of the space that you're radiating. And then you can see here the gain is inversely proportional to your 3 dB beam, right? So the smaller the beam width you make, the larger the gain. The tighter you squeeze the balloon, more it will elevate in a particular direction.
Is that theta, is it the half angle or the full angle?
That's a half angle, and also I don't make that point on the slide, but I believe this is in degrees. Degrees. Please make a note there. The data, it's kind of usually, I kind of follow the book and double check with the book. I believe both of these here are data expressed in degrees, which I told you not to do, but that's what he does in the book. And I'll make sure that when we do problems, we actually pay very close attention to that. That's a very common area where students make mistakes. Let me skip this. I'll go through these at the end. And then some practical considerations. So antennas often limiting elements of the satellite system. This is what kind of is I guess, very important part of the satellite system. Their good satellite antennas are having very strict requirements. It's not uncommon that R&D efforts to put some antennas together can go into $1 million just for the development of the antenna. Later on, when you manufacture it, it becomes much more cheaper. But then again, you don't have too many quantities that you manufacture of those. So there are quite a few, not quite a few, but there are not many places that actually take these tasks and perform the design of satellite antennas. We have one here in our neighborhood. This is, I just thought it would be cool to put it. This is a Ka band antenna, so this is a high frequency, very high frequency antenna that is designed here in Melbourne. And I didn't get it from anybody from here, so I got it just Google. So maybe Josh would point who actually did this work. Right? But what kind of antenna is this? You can see that this is an antenna array. Every one of these is an antenna element. And it would be interesting, more interesting thing would be to flip the side, flip this on the back, and see how do you feed those, right? And I doubt you feed every single one of them. Some of them are probably just passive reflectors that are used to point, to help you shape the beam. But looking at this, you can almost, you can probably sense that designing something like this is extremely difficult. And not only, final result is not that expensive. I mean, there are some cool materials that go into this, but once you know it, then manufacturing is not. But deciding whether this is 55 millimeters or 56 millimeters and what impact does that have is a tremendous challenge, and you have to have very sophisticated tools and a lot of experience to do these kind of things. So that's as far as I guess slides. Let me do a few problems here that illustrate some of these calculations. They're in the notes, so I'll just go through a couple of calculations here along the lines of what you are expecting to do. So it says here, this is example 2 in notes. It says, estimate gain of a circular dish having a diameter of 18 inches at frequency f equal to 14 gigahertz. And assume that the efficiency is 0.6. Now, a lot of these examples that I do are, you can see very simple examples, and you may wonder what's the wisdom of doing that. They're just plugging into the formula. But there are two reasons. First one is, you get familiar with the formulas, you make sure you understand the units. But more importantly, you start building intuitions. What are some things that you expect, right? If I ask you, what is the typical gain of the satellite antenna? Is it 10 dB? Is it 20 dB? Is it 30? Is it even more than that, right? So by doing this kind of problems, you get to build, intuition of what to expect, right? Even particular sizes of the antenna and so on. So let's just work this out. 18-inch is 0.4572 meters. 1 inch, somebody help me here, 2.23, right? Centimeters. Let me not. 2.45, right?
2.54.
5.4. Thank you. My fault. See, I embarrassed myself. But that's because my calculator doesn't work. 2.54 centimeters. So that's the conversion, right? When we talk about the addition antennas, you would always say, in inches, right? Or even feet. Like you say, like you receive that with a 1-foot dish or a 12-inch dish or 22-inch dish, or you talk, and the sizes are comparable to car rim sizes or tire sizes. So you can say 16-inch, 20-inch, 22-inch, and so on. Right? Kind of like what is on the units. So to calculate the gain of this antenna, so here the question is calculating gain. We also need lambda. Lambda is equal C over F. So in our case here, this is 3 times 10 to the 8 meters per second divided by 14 times 10 to the 9 seconds. So lambda in this case is 0.0214 meters, right? So you can see that once you go to the 14 gigabit, that's a KU band, your wavelength is this big, right? It's 2 centimeters, right? So something that is half a meter, and when compared to something that is this small, it's pretty large, right? So this, even for the small sizes of these dishes, you end up with relatively large gain. Relatively
So
large.
should be 1 over a second.
Hertz, right? 1 over second. And now you calculate your gain. Gain is equal to, we said that for, it's going to be your efficiency. I didn't have it. Do I have it here or no? I had a formula that was on that slide, d pi over lambda squared, right? So this is a linear gain. Now, if you want, typically we, as you know, we express antenna gain in dB, which is 10 log of your linear gain, which is 10 log of your efficiency, and plus 20 log of d pi over lambda. So in this case, we have everything we need to have. So it's just a plug in into the equation. So you end up with gain expressed in dB being 10 log of your efficiency, which in this case is 0.6, plus 20 log of the diameter, which is 0.4572 meters, divided by pi, and then multiplying your lambda, which is 0.0214. And when you calculate this, this is a 3431 dB.
So divide by pi or multiply by pi? Multiply.
So it's 34 dB. So there you go. How much is 34 dB? 30 dB is what in linear terms? 1,000. So we're talking an antenna that has a gain that's over 2,000, means that it prefers this particular location more than 2 times than what you would have relative to our isotropic radiator. And then, if you think about the only way that it can achieve that is by reducing the gain in all the other directions. So there's additional reduction in other directions, and a lot of times we talk with front to back ratio. So the front to back ratio has to be even better than 34. It has to be, can be even more than that. So, okay, so, and this is huge gain relative to what we encounter in terrestrial systems, in particular in cellular systems. In cellular systems, we have base station antennas 10 to 15 dB, your mobile antennas, which are essentially 0 dB or something small. Here you have, because you don't broadcast, you're just focusing in a small portion of the space, you have a relatively large gain. The example 3 in your notes says, consider an antenna that has efficiency of 0.6 and 3 dB beam width of 2 degrees. Estimate its gain. Right? So we had that relationship again that that was on a board that I guess we start by saying 3 dB was equal to 75 lambda over D. And then we have also relationship that gain of the antenna is efficiency times D pi over lambda squared. Combining these two, you end up with the relationship that gain of the antenna is 75 squared pi squared A over 3 dB squared. And this is that what I had on the slide, times 5, 55 times 10 to the minus, or rather 10 to the plus 4 divided by 3 dB squared. So this is these are the two fundamental and the derived expression here, derived expression that relates the 3 dB beam width of the antenna with the gain of the antenna. So if I have all of these given, I can calculate the gain of this antenna as being 10 log, gain expressed in dB. Just make that clear here. Gain expressed in dB is going to be 10 log of 0.6, that's your efficiency, times 5, 55, times 10 to the 4, divided by 2 degrees squared. I should really put degrees somewhere here that you know this theta is in degrees. And this gives us a value of 39.2 dB. Again, something that's in 30s, 40s, so that's a pretty large gain that we have with these kind of antennas. Let me go to another example. So this is example 4. It says the Earth is viewed from a geostationary orbit at the angle of 17 degrees. That's really not completely true, right? Because I think we calculated that. Too far. This is what the problem is saying. Assume that this is, let me call this angle, in here. Well, let me call it theta. So 17 degrees, this angle here. Now, if you look at some of the calculations that we did in earlier classes, this is slightly larger. It's like 18, 19 degrees. But what is happening is when you're at extreme ends of this, your satellite is so low on the horizon that you cannot hope, unless you're standing on the top of the highest mountain in that area, that you're going to be able to see it over the horizon. So we usually, even though, you know, when you do some basic calculations, you assume that this is a sphere. Once it comes to practical things, you don't really transmit and receive close to horizon. You kind of go at least 5 or 10 degrees above the horizon looking for satellites. So this angle is slightly larger than, slightly smaller in practice. This is the 17 degrees. then what you end up with just pure calculations. And it says, what are the dimensions of the horn that provides global coverage at 4 gigahertz? So your operating frequency is 4 gigahertz. And estimate the gain, so dimensions of a horn antenna for providing this coverage, and then the gain of the antenna. That's what's needed, so 1 and 2. Now, how do we approach this? Well, we see that we have this relationship that 3 dB is equal to 75 d over lambda. Now, in this case, your objective, if you look at this, the Earth from the satellite, what you see is a sphere, right? So the appropriate horn here will have a circular profile, right? It would be circular horn, right? And it covers the kind of beams towards this sphere that it sees, right? Now, your coverage of the objective is circle, so the appropriate d in this equation is essentially the diameter of that circle, right? We'll look at some problems where your objectives are not circle. Now, if you want to focus on portions of this view that you have, then that is not necessarily always a circle. Sometimes it's a circle, but a lot of times it has a different geometrical profile. So from here, I can easily calculate d as being 75 lambda over delta 3 dB. And
Professor,
yes,
did you flip the formula? It's 75 lambda over d, not d over lambda.
It should be 3 dB over 75. 3 dB lambda over 75.
which one?
The,
Here.
Yeah.
Yeah. Sorry. That's the problem of talking and writing, right? You cannot walk and chew gum at the same time. Or you cannot do these. Yeah, of course. The larger d, the smaller theta, right? They're inversely proportional. And that's what it says here. Right. So I have 75 times 3 times 10 to the 8 divided by 4 times 10 to the 9 and divided by 17 degrees. I had another error that I don't know if you noticed, that when I say 17 degrees, it's from here to here, right? It's 2 times 17, right? 17 degrees is that. So when you calculate, this ends up being 0.33 meters, right? So with the dish that's this big, right? It's not very big, right? But it's not very, doesn't have good focus either, right? Because its beam is relatively wide. It's 17 degrees one side, so that means the width of the whole beam width is 34 degrees. Now the gain of this antenna is going to be, what do we have? This is the relationship that we can use. Or I actually use this one in the notes. So it ends up being the efficiency times 555 times 10 to the 4 divided by delta theta 3 dB squared. In our case, this is 0.6 times 555 times 10 to the 4 divided by 17 quantity squared, and this gives you 115.22, which is 20.6 dB. So that's the
efficiency come from.
Efficiency comes from
Assume that's given.
assume, right? So assume efficiency of 0.6. So this kind of gives you the lower end of the gain, right? Because I mean, you can make the antennas of a lower gain, but what that would mean is that they would have a lot of energy being wasted because it's going to be missing the earth, right? You don't want anything that has wider beam than 17 degrees, wider 3 dB, because that means that it is radiating past the globe, right? So this kind of puts the lower end on what the antenna gain should be. And then once you start focusing in the portions of the globe, then the gain goes from there. Theoretically, it can be as large as if you want to pinpoint a really, really small area, then it can be very large. But practically, it kind of goes into 30s, lower to upper 30s, sometimes 40, but very rare. Like 30s is what we are, in the C-band. And then let me quickly just go. I'm not gonna do example because we don't run out of time. But what I'm gonna do is just point out some physics here. It says in the problem, this is one of the problems from the book. If you look at continental U.S. from geostationary orbit, this is 6 degrees and this is 3 degrees, right? So now we're, instead of radiating across the entire globe, we're now looking at the objective, which is just a section of the globe. And it says, well, how would the horn look like that would accomplish this? Now, what you need to remember is the horn that radiates this way has to be like this, right? Ability to focus energy, in this direction to be smaller means that the dimension across this direction needs to be larger, right? So if you start from circle, right, and or let's say start from square, right, that would have a horn that's square in profile, and if you start making your objectives this way, meaning that you need to be more selective in this direction than in this direction, that means that your dimension in the direction where your selectivity is larger needs to grow. So if you want to focus the energy in this direction, your dimension relative to the lambda in that direction needs to be larger. So the horn that would accomplish this would look like this, right? Relative. So it would be longer this way, so your d over lambda in that direction would be larger. Therefore, the beam width would be squished that way, and then it would be less selective in the other direction. And if you follow the example here, you end up with a horn that has the dimension east-west this way of 0.34 meters, and the dimensions north-south, which is twice that. So this is smaller. Twice because this is 3 and 6, right? That's the one is the twice of the other. And then the gain of this antenna, if you were to calculate, we're going to use this times 4 pi over lambda squared times its physical size. And this is a rectangle, so this becomes times 4 pi, and lambda, this is what is lambda here. It's 11 gigahertz, so frequency here is 11 gigahertz. This is again K band. So lambda is 0.027, and then squared, and then what I wanted to say here is A is going to be your 0.34 times 0.68. Right, and when you do the calculations all the way, or when I did them, you end up with 33.7 dB. Again, mid-30s as a gain of this antenna. Okay? Any questions? Go through these examples, because as of next class, we're starting working on the link design, essentially the link budget calculations and all the things that we need to take into account when we're doing dimensioning of the link, signal to noise ratios, and noise calculations. And part of the lean budget design is the decision of what antennas to use, with their dimensions and gains and beam widths and so on. So this will be part of it. Okay.